Okay, looks like we've got a lot of people joined in already, so let's go ahead and get started. Welcome to today's webinar on structural geology and mining geotechnics from data to decision. We've got our panel of experts here today who have been very gracious with their time, and I will introduce them formally in just a moment. But before I do that, I'll give you a little bit of background on the Geotechnical Center of Excellence. We are at the University of Arizona. We're part of the School of Mining, Engineering, and Mineral Resources. We are an industry-funded group, and we are member-led, and we're a very interdisciplinary center. So we bring a lot of different disciplines into the field of mining geotechnics. And in doing so, we conduct collaborative and practical geotechnical research and education such as this webinar that we're presenting today. And we pride ourselves on bridging gaps between academia, industry, and fields of study. Here's some fun pictures of us. We do a lot of outreach as well. So some pictures of us doing some outreach. As I mentioned, we are member funded and member led. So here is a snapshot of our wonderful membership group. Huge shout out to them. Without their support, none of this would be possible. So big thanks to them. If you would like to learn more about being a member of the GCE, you can reach out to any of us at the GCE on LinkedIn or wherever, or you can email us at gce@arizona.edu. That's probably the most direct way to get a hold of us. And maybe one of my colleagues can put our email in the chat for you, just so you have it available. So this webinar is based on one of our professional development courses, Structural Geology for Geotechnical Professionals. Like all of our courses, they are fully online. They are recorded video from our experts, industry experts. And this one is a 12-week course. However, the content is available for a full year. So you can see that the course began on June 10th of this year. So that was 3 months ago. But if you join now, you still have 9 months or so to complete the content. So if you'd like to learn more, you can scan the QR code here. And I'm going to advance to the next slide, but one of my colleagues can also put a link in the chat for that as well. And the structural geology course was underwritten by the Large Open Pit Project. So a big shout out to them for their support in building the course. It was took a real team effort. And as always, thank you to our panelists today, our course advisors, our collaborators, everybody that helps us build all this wonderful content. Just a couple of housekeeping notes before we get started. So if you're joining today, you are muted and your video is off, and you won't be able to turn either of those on, so don't worry about it. If you'd like to ask a question, which we highly encourage, it's the whole reason for this, please use the Q&A function in Zoom. You'll see a chat function and Q&A. Use both, but if you have a specific question, please use the Q&A. That's the one we're kind of actively monitoring for questions, so we appreciate that. Your questions can be anonymous, and if you see other questions that you like from other people, you can give them a thumbs up, and we can high grade those. This is a recorded webinar, and we'll post this to the structured course site as well as our YouTube page. And just a quick disclaimer that the views and opinions expressed by our panelists are of their own and do not necessarily reflect those of the GCE or any affiliated organizations. All the content is intended for educational purposes, and it is not intended to be a substitute for site-specific professional advice or analysis. So thank you for bearing with me through that. So let's start with a couple of introductions, starting with the GCE team. I will be your moderator. My name is James McNabb. I'm a senior research and development engineer at the GCE. I'm joined by Julia Potter. She is the director of the GCE. Hello, Julia.
Hello, everybody. Thanks so much for being here today.
We're also joined by Benjamin Meyer. He is our research and development software engineer. Hello, Benjamin.
Hi, everyone. We're so glad that you could join us today. We're looking forward to it.
And we've also got Cheryl Bukowski. She is our professional development program lead. Hello, Cheryl.
Hi, everyone. Thank you for joining us today.
All right, thank you. So they will be working hard in the background to make sure everything is running smoothly and fielding your questions and so on. Okay, so let's introduce our panel, starting with Wayne Barnett. He is a principal structural geologist with SRK Consulting. Hello, Wayne.
Hey, good morning from Canada here. Thank you.
All right. Next, we've got Jeff Owen. He is a manager of structural geology at Tech Resources. Hello, Jeff.
Hey, good morning, everyone.
Next, we have Luca Zorsi. He's a principal geoscience specialist with WSP Canada. Hello, Luca.
Hello, hi, everyone.
And then from the other side of the world, we've got Ian Besson. He's a principal member of Tech Geological Consulting. Hello, Ian.
Hi there.
Thanks for joining. Hopefully it's not too early or late for you. Not sure which one.
It's fine. It's fine. All good.
Great. Okay, so let's get started with a kickoff question, sort of a broad topic here. How do you balance the richness of structural data with the need for clear, actionable inputs for engineers and decision makers? And this is something that comes up quite a bit in our industry. And just to get things started, how about I'll start with first person I see on my screen, which is Wayne.
How do you balance the richness of structural data with the need for clear actionable inputs from decision makers? Well, I think by having enough data, to make decisions, you need to have geological understanding and models that are reliable. So you need to make sure that you get enough structural data to support your interpretations and models. So I don't think there's necessarily a balance. You need to make sure that the quality of the data that you have is appropriate, that you understand the system that you're dealing with, and make sure that you've got a reliable understanding of where the inadequacies are with the amount of data you have versus the data versus the parts of the model that you really understand and have reliability for. Yeah, I'd like to see if someone else has got a clearer answer to that.
Yeah, thanks, Wayne.
Yeah.
I mean, go, Jeff. Go, Jeff.
Okay. Yeah, I guess just some thoughts. I was working on a project not too long ago, and I mean, it's a great question, because the question was, how do we balance out the structural data for the inputs for the engineers? And I think one thing we ended up doing was trying to really define the scope from the engineers. And so by putting it back in their court, we were able to learn, do they actually want brittle structures that are very multi-bench in scale? Do they want maybe smaller structures and maybe like 150 of them to help find the rock mass? So I think for us, just an example I can think of recently, it was really defining, first of all, understanding what they wanted. And then what we did from a structural perspective is we have these templates or these standards that we use, but then was modifying the template just to make sure that we actually, the structural richness, as is phrased here, great phrase, trying to make sure that in our template we actually help collect the correct data to help assist in the scope that, or the deliverables that they needed moving forward. So I guess those are some thoughts from my end. And I guess, in addition to that, maybe the structural data, like if we're geotechnically specific, you might be looking at things like, I mean, I can accredit Wayne for this, right? Like I feel like we're part of the structural geology family here because he's helped us a lot in the past. But collecting things such as damage zones, fault characteristics, infill characteristics, and persistence and importance of structures are some of the things we put into our templates to help the geotechs in their decisions. But then outside of the engineers, now I'm rambling, you have a number of other stakeholders as well. I think just being able to modify those templates to make sure that you're having a fit for purpose model. Is it something for resource estimation where you might be looking at something that's cohesive or competent, constraining grade a bit better, or is it more geotechnically specific that's more brittle? And in my opinion, you don't necessarily always have one model that fits all. I thought.
Yeah, just to add to what Wayne and Jeff just said, it's just also the other aspect in which make sure that there is a full understanding of what your data on the geology and structural geology side of things mean for the geotechnical team or other stakeholder, meaning that there is a full understanding on the end user of the structural data or structural model, what that model means and what are the correlation with like the inputs that they are using in the geotechnical design, for example, with the geological interpretation. So there is full interaction and understanding of what type of information is provided from the structural or from the geology side of thing, and how that is used for geotechnical inputs. It has to be, in addition to collecting in the right way, providing in the right way, is also the communication to making sure that a specific wake zone can be explained geologically by this, and this. So there is always this dual correlation between the two, which sometimes it's kind of like missing. And it's also on the geology side of thing and making sure that things are communicated and explained the right way as well.
Yeah, if I can add to that, I would say in a more general sense, to try and characterize in terms that the engineers and decision makers can understand a feature, a structure, a domain, etc. Firstly, then secondly, to build that in 3D space with enough supporting data. Thirdly, to try and find where there may be variations or step changes or changes in orientation of a particular feature, affiliation or a bedding, which will then guide you towards where your domains or where your geotechnical domains might be. So we're at the interface between the rock and the engineer. So it's our job to try and communicate that. So I agree with everything that's been said, but communication is essential. It's not just enough to show them a stereo net with a robust data set that's statistically significant. You need to communicate to the engineer what that thing means. We're dealing with natural systems. It's not a building or a bridge. So for us, it's necessary to communicate properly, to provide that handover to them. You don't just drop the report and send them your invoice and then walk away. That's very, very important to make sure they understand what you're trying to get across. So they don't go off on a tangent. What would be even better is if that once they've done some kind of analysis, and we work with Itasca a lot, is to come back to us and say, well, this is the way we've taken it downstream, in discrete or finite element modeling. What do you think? There's often little tweaks that can still be made at that point where, you made a mistake where you've taken a fault through an unconformity, for instance, where you shouldn't have, so cut it off there. The model should show that anyway. But things like that, it's really about the interface and communication. For me, I think that's the most important thing.
I really like Ian's comment there about the communication, and I think one of I'll mention a challenge that we've had or I've had in the past is going in and collecting this information that I think is fit for purpose, creating a 3D model out of it and handing it over to a geotechs or a consultant, and then thinking, awesome, it's been communicated, nothing can go wrong. And then you find out like a month later or 2 months later, there's just been some misunderstanding on the cross-cutting relationships, or somehow things get tweaked or adjusted, or a structure that was meant to be for one purpose is used for geotech, and all of a sudden a haul road is being designed in a certain area. So I really like Ian's comment about the follow-up, I think. And I'm interested if others on the panel here also have experiences with this or want to expand on this, but I think that follow-up comment of like, once we hand things over and being able to reach out to the consultants and kind of maybe create like a follow-up routine, just touch base with them once every few weeks or every few months. So I think that's great.
It is Jeff. We found myself in that same situation, and it especially when the models or the interpretation are used for advanced design, specifically when Ian is mentioning Itasca, so advanced numerical models. There has to be like a two-way discussion, especially during the setup of the numerical simulation, because that's where things can go wrong pretty easily. Especially even if we assume that the model has been fully communicated in the right way, because there is a lot of things that maybe we are not aware on operational issues like size, meshes, and a lot of sort of thing that needs to be considered as part of the numerical simulations that could have an impact on how some of the structures that we have interpreted will be represented in the numerical simulation. The easiest one is that, we do see structures that are very thin, or like we're talking about less than a meter of damage zone in total, and so the core is even thinner, and then they show up as this 20-meter zone of very weak rock in the numerical simulation, because that's the mesh size that they're using. So there has to be then an additional, constant communication to make sure that, we're not overblowing the interpretation during the numerical simulation, that it's not representative of the reality. So it is a two-way challenge, that it doesn't stop as a model gets communicated and then we're walking away. There has to be a more constant communication between the two teams. And I just add this, and then I stop it. The other major issue is communicating when we're trying to find the best way to, communicate the uncertainty, because we all use this reference guide for confidence with interpretation, low, medium, high confidence in the interpretation of specific wireframe. But then we have seen that we need to sort of change the way that has been communicated to avoid that, the assumption made by the end user is that, okay, I don't use anything that is lower than a medium confidence, and I'm just using in the model everything that is high confidence without considering everything that is low confidence, which is, it's a normal thing that happens, and it's the wrongest thing that can happen. That's why there has to be a constant two-way communication, even when the numerical simulation it's set up. If I'm just using the slope stability numerical simulation right now, but it's applicable when we're talking about hydrogeological modeling or geochemical modeling as well.
Yeah, it took me a while to fully understand the question, but it is very. The LOP guidelines actually, even include that very important point that at the end, you really have to sit down with your client and communicate exactly what your understanding is of the product and how it makes sense for that client's objectives. It's best practice.
Right. Yeah, thank you all. And I think there was another question, the next one that I was going to go to, which is very similar. I think you guys touched on this quite a bit. What measures can be taken to ensure that uncertainty in structural data is properly communicated as it travels from the geologist's hands up through the ranks? I think we discussed generally communication. What about the kind of details of a model or something? Are there things that you can add, like widths of damage zones, or any other sort of things you can add into a model to communicate uncertainty?
I got to stop on this one.
Yeah.
So it's to me, it's a multi-level thing. So it goes down to the detail of a single wireframe, what we don't know about that wireframe based on data distribution, based on the way that we're connecting the dots, based on how that wireframe relates to the overall conceptual understanding or geological evolution or the interpreted geological evolution of the area. So there is that one. But then there is also other higher level of uncertainties that get dragged into like the final product, hence the model, that in some cases can be quantifiable. So we can come down and put a number to it. But in other instances, you cannot quantify that because it's part of the randomness of a natural system. And so it's more like, to me, it's more like an open discussion to fully provide an overall a system-wide, and by system-wide, I mean from the data analysis to the interpretation to the final model, like an overall description on what we don't know at each step of the workflow to go down to the final model. The example that I always use is that we can have a wireframe that is constrained by a data point a wireframe that might be 200 meter long, and you have a data point every 10 meter everywhere, but all your data points are not trustable at all, and you have no idea about the geological setting of the area, that wireframe, it's not reliable, even though it's fully constrained. So, and that is the trick that sometimes gets missed during the collaboration or discussion with the final stakeholder. Even if it's written down, even if it's fully described, then somehow there is something magical that happens in between. That model, that wireframe gets taken and becomes the truth and nothing but the truth, forgetting everything that is an interpretation. And that interpretation also is influenced by my personal background, my experience in structural geology, that it's different from Jeff, from Wayne, from Ian, and that it's normal nature that we try to sort of like interpret and connect the dots based on what we're more familiar with. And we are describing only what we know and what we see, but we cannot fully describe what we don't know. We could predict. And so every time we don't have data between boreholes, we're making a prediction. And then obviously it depends on the geodynamical setting. Non-deformed sedimentary sequence, you can get away with that, with wider space data point. But if we're talking about, I don't know, polydeform metamorphic sequence in the iron ore sequence in Eastern Canada, even 50 meters between two boreholes, anything can happen in between the two. And fully representing them into a 3D model, it's very complex. So, but sometimes that sort of uncertainties, I'm simplifying the discussion like insanely here just for the sake of time. So it's always tricky to fully represent uncertainties because your certainty at the end of a model goes down with everything from the beginning, right? From your data all the way to how you interpreted the data and all the way down to how you model the data, without even touching the fact that the wireframe could look different if you model it with Leapfrog instead of MapTech Vulkan or DataMine, because there is that part too. So there is also the interpolation method that can induce additional uncertainties between the data points too. So it's a multi-level thing. It sounds like that we cannot do anything about it. No, we can try to work to contain what we can control, right? Where we can say, look, the data doesn't work in here. The data needs to be adjusted, or we need more data to close the loop, or to sort of like from 3 or 4 different possible interpretation that leads to go down to 1 or 2, and sort of like that's the way that we could approach this. And then, I'm throwing it in there, which is something that I always say, is that our colleagues in hydrogeology and geotech are allowed to do a lot of sensitivity analysis when they don't know things, right? When you don't have a lot of data, you can do a sensitivity analysis. But somehow, when we're building a geology model or a structural model, a model needs to be developed, right? I understand the implication downstream, but the idea of approaching that probabilistic or stochastically to provide variability or possible I'm talking general. There are specifics in which you don't need that, but there are some stages in the project, or depending on the risks or the overall complexity of geological system, in which that could be a way moving forward that we could start to think about, of approaching it probabilistic and try to quantify a little bit some of the uncertainties that can be quantifiable. Because let's be clear, there are a lot of uncertainties when we're dealing with geological modeling that we won't be able to quantify. The randomness of nature, that is impossible to quantify.
Yeah, if I could just chip in here, I mean, just, economics drives everything. So I mean, engineers are in cahoots, if you like, with the CEOs and the mine managers. So the vast majority of drilling is predicated on hitting mineralization, right? So most of the drilling is designed to hit grade, and most of it is not logged properly and not, super useful for us as structural geologists or geotechnical engineers. I mean, we'd be lucky if 10% of the drill holes in any deposit have, super useful information that we can build our models on. So very often you tend to find yourself picking up straws and as Lucas says, trying to interpolate and infer over quite long distances as to what's happening in between. Sure, you can maybe build your country rock model, but in terms of characterizing structures and the faults and maybe which fault offsets which is very difficult. So yeah, I always come back to the question: does uncertainty have a unit, and is it 1 over confidence? Does one uncertainty unit equal 1 over confidence? So to me, it's always a bit of a it's not vague, and I think that the rest of the people on the call do a better job at quantifying or semi-quantifying this than I could do. But unless you communicate properly with the client, they can go away and have the wrong idea of what you've built with them. So uncertainty to me is a very touchy, kind of almost fuzzy thing. And I know everyone's working on reducing uncertainty. Engineers, CEOs, and mine managers, by their DNA, don't like uncertainty. But us as natural scientists, we're more accustomed to dealing with uncertainty. There needs to be some kind of, synapse or bridge between those two.
Can I jump in as well? Yeah, great comments from Ian and Luca on this. I was gonna. One of the things I think is available for the audience here is there are some slope stability papers, if through the GC, if I remember this correctly, that actually discuss a bit about putting confidence on wireframes in your models, right? So expressing your confidence when in your data collection, how do you pass that to stakeholders? You can do distance to data heat maps and put on your wireframes. You can also put a color map based on a different level of study you're at. So for example, if you're at a scoping level versus operational level, there's ways that as a structural geologist, you can actually color the wireframes that you're developing and passing it on to different stakeholders. And I think there are papers available through the slope or through the GCE for people if they want to follow up on that, which might help with some of the communication. And then I was just thinking of one thing though, and it's a question that often comes up in our group anyways, and I'm really interested in what the panelists think on this. If we're going into an area and you're creating wireframes in an operational environment for geotechs, if you don't have a lot of data for a certain area, there's always, I find this constant conversation where a geotechnical engineer, often my conversations are, can you please put a structure in there, even though there is that much data, just so we can plan for some sort of uncertainty or plan for some sort of scenario. But then I've also seen that if we do put a wireframe in there, it sometimes becomes truth. And then all of a sudden, again, you're modifying haul roads and plans. And so my feeling is sometimes this communication of uncertainty in the data is just don't put a wireframe there. And then you really are highlighting that you need a bit more data collection. But I know that that's just definitely going to be an audience that highly disagrees with that and wants to go with the put something in there so you can plan for the worst. So I don't know if we have time, but I'd be interested in hearing what the panelists think on what their experiences with that.
We've got plenty of time.
We've come across the same thing, Jeff, and I think that you're quite right. If you do that, you put in something maybe that's false into the model. But the really the underlying problem is that once the thing's on screen and everyone's rotating it in 3D and oohing and eyeing over it, people forget about the report. So the report is where all the provisos and the disclaimers and the limitations and the caveats are listed, and that gets filed away, and everyone just looks at the model. But the real juice, the real meat is in the report. It's not in the model. So I like the idea of trying to color your wireframes to somehow, get across that, that communication. I mean, maybe there should be sort of a way we can build wireframes, and then when you first open them up, a list of questions pops up from the report, and if you answer them wrong, the wireframe just turns into little butterflies and disappears. If you don't get enough of the questions right, somehow force people to read the report to really understand what the thing is that they're seeing on screen. That's really, to me, crucial. And then that means that the better your report can be, the more confidence people will have and the less uncertainty there will be in the model. But really, the report is where it's at, I think.
Yeah, that's good. And one thing a colleague taught me just the other day was when you're building these models, and let's say you're using Leapfrog, you can use different types of data or points that control the model. Let's say disks would would be strong information because there's actual measurements, and then you put dots controlling the direction of the wireframe to to illustrate that it's a lower confidence that you don't have any data there. I thought that was quite a good idea. There's ways.
That's an interesting point you bring out. We've recently, well, not recently, but a little while ago, discovered that Leapfrog has a hierarchy of controls according to. Yeah, you know that, right? So drill hole is king. Contacts and drill holes are king. And then you get a sort of a decreasing series of sort of gravitational weights that pull surfaces in various directions. And those are your structural disks, your form lines or your form surfaces that can have a, blending trend between two contacts and all sorts of other things. None of those things result in the surface being snapped exactly to them, but they're kind of like, like a black hole sort of pull the surface towards them. So there's this hierarchy of controls that Leapfrog is quite coy about telling us how they really interact. And unless we can quite figure out how those interact, then this whole thing about uncertainty and confidence becomes a bit of a moot point, because the software is now doing a push me, pull you maneuver on you that you might not be quite getting. So that's also another thing that's perhaps a separate discussion.
Yeah, and let's not forget peer review is a good way to solve this. Yeah.
And just to add, Jeff, to similar, it's kind of like a day-to-day interaction that I also am exposed to this, right? And we were in some instances were resulted into like not calling the wireframe as a fault. Like literally in the name of the structure that was generated, it was not called a fault. It was called either a lineament or something. And, that wireframe got broken down into specific, 2 or 3, whatever segments based on if there is anything that could highlight the present. Like if in topography, we can see a lineament, there is a section that is called lineament, and then an extension on the side saying there might be something in there for planning purposes, because we did face the opposite, not putting anything, then turn out into there was something at the end and it was a big blow, right? So there is also the other side of the coin, that you don't put anything even though you see something, and then there is actually something that wasn't planned ahead. I always found myself in a situation in which the worst case scenario was considered, in which the client wanted to see, okay, what if there is something in there, to plan accordingly, and if there wasn't, then good. But we were, one of the trick was not calling it as a fault, calling it something completely different, even in the wireframe name, and obviously describe it in the right way in the matrix or in the catalog that goes along with a wireframe, right? So that's kind of like, it seems like a basic trick kind of thing, but without going to fancy digital ways, but that kind of was the trick of solving that sort of issue.
Yeah, it's great, Lucas. So you're saying like for a wireframe, you would say inferred, right? It'd be like northeast structure inferred kind of thing for all of
lineament, or like northeast lineament. That's it. That's what it is, right? So without saying what it is.
Yeah, there's also ways being applied where the density of data points, you sort of calculate what is that density, and it gives you, in theory, it gives you some idea of okay, more data points, the more reliable. Not necessarily true, but it's just one way of approaching it.
All right, that was a fantastic discussion. Jeff, am I remembering correctly that I believe Neil Seifert had a paper presentation on creating heat maps on wireframes?
Yeah, that's right. I'm trying to remember if that was in Brazil or Tucson, but I think it was Tucson. So that was 2022, I think.
Okay.
Yeah. And I feel like, I'm not sure, I feel like SRK had a distance data map as well, if I'm not mistaken.
Yeah, great. Yeah, we'll see if we can pull those up and put them in the chat. All right, great discussion. We've got a couple of live questions. Let's go to this one here. This is an insightful question here. It's 2 parts. In open pit mines where country rock is poorly documented due to ore-focused exploration, How should we approach fault mapping in heavily fractured zones with brittle and shear structures? Should we prioritize major, larger faults and filter out minor ones to avoid overwhelming mine planners with too much data? And then question 2, when faults are visible along high walls, should we map only the exposed face or extend the faults beyond it? How can we determine a reasonable extent if we're projecting faults into the model? I think these are great questions and probably questions that a lot of people have as they're mapping their mines. Anybody would like to jump in on this?
I don't mind. I mean, Wayne will back me up on this, but I mean, fault mapping is obviously you're determining a collection of features that denote a zone of weakness or displacement, right? So the question is, what is that bag of features that tell you something major is happening? It's offset of your stratigraphy. It's fabric embrittlement. It's alteration. It's dilation. It's apertures, etc. There's a whole bag of them. So should we prioritize major, larger faults and filter out minor ones to avoid overwhelming mine planners? Well, it's not the mine planners that you have to worry about. It's really the geotechnical engineers. So the mine planners are sort of a bit downstream of that. There does come a point where, when you say minor ones, there does come a point where you're sort of looking at these things and saying, well, I can only see them on one bench. So maybe they're going to cause a wedge failure or a local toppling failure or loss of bench definition. Those, I would say, maybe you can address by bagging them into a structural geotechnical domain and using, fracture modeling or discrete, or what do they call it, DCF? What is it called? DFC? DCF? Help me out here. I wrote a paper on this with Marnus Bester, and I've forgotten the term. But basically, there is a limit as to where you're kind of tending towards small fractures, and you really shouldn't have to plan around those. So there is a sweet spot between the things that you really want to characterize a model and the ones that you maybe want to bag into a domain within a particular rock type. So that's what I'll say for that one.
Yeah, I support that. I like to try and map everything, but you can never do that, right? So, yeah. Well, I think with these drone scan imagery, we can probably do a lot more detailed work. In terms of overwhelming, well, you do obviously have to focus on what you think the highest risks are, and if you've got large structures that are potentially a risk of causing slope instability, then you got to focus on making sure that you really understand those larger structures best, and what are their properties. Bench scale structures, it could be little wedges, etc., as Ian pointed out. That they can also be important, but clearly you got to focus on what is going to be the biggest risk to your slope.
Yeah, I think, and I don't want to be parochial and nasty about this, but I think there's also, it does depend on the development of the mining industry in that particular country. So you can go to certain countries like in the Middle East where they think, if you look at it, if you see a displacement in core, they'll call that a fault. So they think every offset equals a fault. But if you kind of, end up in Canada, that kind of thing, they've kind of got through that phase, and they know that that's not a fault. And they know that even something on a bench scale, you could just maybe bag it into being a joint with minor displacement or something like that. So there is a degree of kind of maturity in the way that structures are mapped and viewed in the pit, depending on where you are in the world. And if you're in a more developed mining industry like in Australia or Canada, there will be a sort of and again, I don't mean to be mean, there's a more mature view on what you should map and model, and a less of an obsession about the small stuff, and then you have a bit more carte blanche to go about your business. So I don't know, maybe that's a bit cruel, but that's what we found.
Great.
James, just
Go Jeff. Go Jeff.
I was just going to add on. I think you had a second part of the question there. I think, James, was it extending faults behind the pit wall. Was that?
Yeah. Yeah. When faults are visible along high wall, should we map only the exposed trace or extend the fault beyond it? How can we determine a reasonable extent for projecting faults into the model?
Yeah, it's a good question, and it's obviously you're limited by your data to some extent, but I think one of the things that I lean towards doing is if you have a bit of a structural understanding of your deposit, what the structural architecture is, and have an idea in your head, I guess, of the timing relationships and cross-cutting relationships. If I'm seeing a structure in there that seems to match a certain structural style or a certain structural regime, I'm going to use that knowledge of the deformational history to extend that structure to a point where I think it might be truncated by another feature or vice versa. So I'm not sure if that makes sense what I'm saying there, but yeah, obviously using whatever data sets you have, drill hole data, geophysics, but then of course for me, cross-cutting relationships if all else fails and trying to terminate or extend based on that, just as a best case scenario, best guess scenario.
I have go for it, Lucas, sorry.
Oh, no, it was just like two quick comments on what you discussed on question one. And, really the prioritization of larger or smaller scale faults, it all depends on the scope of your mapping at that point. The small scale structures or the smaller one, as Ian was hinting, like they could be very important for your bench scale analysis or your stability at the bench scale or a couple of bench or even like an interramp level thing. So it really depends on what you're trying to achieve. But pinking down the major one first and then working your way down to the smaller one, it's also like a good approach as well. And to add what Jeff, just to stress what Jeff just said for question two, that is the whole point of when you're doing a model. Know your deposit, know what you're dealing with, and if you know the geological, or at least you have an hypothesis in your head or a theory in your head of the geological evolution of the area, that could guide you on how to extend the fault beyond the pit walls, assuming obviously you have available or not available a lot of like subsurface data like geophysics or borehole. Because a lot of the times we do see situations in which somebody maps, sees a fault, and then they build a wireframe out of context as well, and just for building something for operational purposes, or they lack in sort of like the background on the geological system that they are dealing with. And so know your deposit, know your area, have an idea about the geological evolution of your area or the expected cross-cutting relationship, and that could help in making those decisions when maybe the data it's not widespread.
Yeah, and then that includes, you're looking at your rock mass, do you get a lot of segmentation on your faults? All right, that gives you an understanding of, okay, well, maybe how far can you project that in your model? In my opinion, though, in general, is I don't know, I'm going to be more conservative when I build a fault. If I'm interpreting the extent of a fault in a model or for a pit, I'm going to be more conservative, and I'm probably going to make it more continuous unless I have information or an understanding of the system that is more segmented and less continuous, and then I will try represent that. So try understand the continuity and scale of your faults.
All right, very good. That was a great question. Thank you for that, whoever posted that. Thank you for the discussion. Actually, a really good lead in to this question. We discussed this a little bit, and maybe we can come up with some specific examples. This is from Nathaniel. How can scientific visualization, geophysics, for example, seismic, electrical tomography, be used to reduce uncertainty in 3D geotechnical modeling? I would appreciate practical examples. So we mentioned perhaps using some geophysics to extend faults behind the high wall in the previous case. Maybe we can come up with some specific examples of how that might be used.
I'd like to just take it from the top down and say that the real use, I think, of geophysics is the regional picture, right? Because everything starts off at an exploration stage, and that'll help you get your eye into what the deformation events are, the kinematics, what is deformed ductilely, what is intruded, late in the system, etc. So for me, geophysics is useful in terms of what are your rock types or your proxy geological map look like? What are your cross-cutting relationships? What is your style of deformation? What might be your cross-cutting relationships between your various structures, and what is your fabric doing? So I think that's what your regional big picture geophysics can show you. If you are lucky enough to have very high resolution geophysics over a mine, which to be honest is quite rare because a mine has lots of metallic things if you're doing aeromag and other, lots of resistive things if you're doing resistivity. So you often don't have those fine granular data sets after mining has begun, unfortunately. So for me, geophysics is really useful at a very, very early, preferably pre-mining stage. The second comment about geophysics, seismics, and electrical tomography is that they've done it at a particular line spacing or data or sensor spacing, and that spacing is nowhere near the resolution or granularity that we can map at in the pit. So you can use them, but just remember that they're broad at the scale that you want to define things at when you start mining or geotechnically designing.
And maybe I have more than an answer to this question. I have a question for the other panelists. Aren't we maybe underusing some geophysics tools like active seismic, for example? Shouldn't we use that a little more in mining to get full better picture of what we're dealing with in terms of structural geology and geological complexity in general? Like it's an open question because I haven't seen a lot of active seismic. The passive seismic that I've seen, it's very broad. Yeah, and as you were saying, like it's okay for large scale and bigger picture sort of thing, but it could be it's a tool that more than other tool like electrical tomographies or could actually allow to investigate, I'm talking about seismic, active and passive, to investigate the rock mass a little better. But I feel like we're not using that at its full potential, and we could do way better too if we would start using it more.
You're right, because I know that in South Africa on the deep level platinum and gold mines, there's an active seismic monitoring system that picks up live things, so if there's a bump, they know exactly where it originated from, where the epicenter is from. But it's used to basically, rush a team of rescue people to there to go check out things, or a safety crew. It's not used to update the model or to inform geotechs, not really, as far as I'm aware, but I speak under correction, but yes, we could use, especially seismics, a lot more, I think.
All right. Wonderful. Great. Thank you for the question, Nathaniel. So we have quite a few questions on AI, as we usually do. So I'm just going to grab one of them. I think they're all relatively similar. This is a live question. Can AI take out the jobs of structural geologists in the future through high-resolution cameras/drones and applying machine learning algorithms from the experience of hundreds of experienced structural geologists? And I think one of the other questions was similar, but it involved modeling as well. So what are our thoughts on this? It's an evolving landscape.
I gotta stop. Great question. Right now, they are tools that could help us a lot, like for data processing, mapping, automatic mapping, testing ideas, possibilities that I was mentioning earlier to move towards more like a probabilistic approach when we're doing the modeling side of thing, or to test ideas, right? Will they take out completely the jobs? Maybe not, because AI works with data So unless we're talking about everything that is done automatically from top to bottom, that it's a different story. But I could see still that experienced structural geologists, that field geologists, their presence is still fundamental to understand whether or not what comes out from the model makes sense or not. I mean, some of the recent tools, they're doing a very good job, and they can help cutting the modeling time and allow to understand or put together different layers of a lot of different data sets to understand trends, patterns, and locations and such. But they're still, you still don't know whether it's fully realistic when it comes out. There's still the need of your input, right? That doesn't mean that they're not useful. They are useful. AI is helping a lot, and because you can dump into a lot of more data sets to try and look for patterns, try to make predictions. But I still see them as tools. So I'm not expecting a full-blown, wiped out of jobs in terms of structural geologists, but maybe they could help us go back to basics and spend more time understanding what the data means and come up with better interpretations, and not spending a lot of time in collecting specific data. Whatever can be collected automatically can be collected through AI, but we can do a better job in testing idea or come up with more robust conceptual ideas on a specific site, and then transform that into a 3D model. That's my thought as of now, but I could stand corrected in like 6 months time, right? So this is how fast it's going right now. But I'm happy to hear what the other panelists have, their idea.
Yeah, they're going to have Luca GPT soon.
Well, okay. Can AI answer an email to an inquiry from a client? Can AI read the scope of work and put together the items that need to be addressed? Can AI write a report that is understandable to the client? Can AI do a workshop that hands over the model so built to the client? Can AI reasonably answer questions post handover to the client? I don't think it can do any of those things. So I come back to Luca's comment that AI is a tool, but use it in parallel with NS, which is natural stupidity. Okay, which is the close cousin of AI, and that's what we do. We are learning machines that use experience to do our work. So yeah, AI is just a tool. So is machine learning. We drive it. We switch it on in the morning. We turn it off in the evening. So yeah, buyer beware. That's what I would say.
I'll throw in a little bit of a contentious side to this, maybe. I think there's a chance that AI, it's a tool. I think there's a chance it's actually going to take away a lot of our mundane tasks, which I'm actually kind of happy about in some sense. Like sitting there, I don't know how many people have sat and picked Televiewer images for days on end. AI's getting to the point of doing that, or RPD, fracture frequency, mechanical versus natural. We're working in that space, our team, and it's absolutely mind-blowing just how accurate machine learning, computer vision can be on that front. So I think I'm kind of cautiously optimistic that it might actually help us to maybe eradicate some of the more mundane tasks, but again, to the point of it being a tool, I think, so a lot of these tasks maybe AI can remove from us. Like, for an example, we had one project where 150,000 meters of imagery was analyzed in an hour, and that would have taken months and months for a geologist. So I think there's huge benefits, but then the next step, and I think the industry is going this way in a number of different countries, but a lot of us have to operate under a certain governing body, and to ensure that we have a bit of a professional approach to the products that we're producing. And one of those things is actually ensuring that the software that is used, we're liable for that. And so I kind of see one of the things we'll need to do as structural geologists. We do want to make sure that we're aware of what AI is doing because it's something that's consistent and it's auditable, which is great. But it's something that I guess in the end, if AI is providing something, we're I guess ultimately responsible for it as well. So yeah, it's such an incredible. We could have another whole presentation on AI. I think there's so much exciting stuff going on here. So.
No, Jeff, I'm fully on board with that. Like all the mundane stuff, bring it on with AI because there's a lot of, that's what I was saying, that it's a great tool that could shift our attention from actually making sense of the data rather than spending hours and collecting them and don't have any time afterwards to make sense of it, right? So that is a pretty good tool. But you're right, you're bringing like a good point though, that at the end of the day, who is going to sign off on anything that AI has developed, right? So you could see discussions that are happening right now in the professional organization, especially when AI is used for actual designs, that people are like, I'm not signing it off. Like, I don't know what is happening in that black box. It looks reasonable, but I'm not signing it off right now, right? So despite all of that, so that is the open discussion would be this, and who is taking responsibility at the end of the day on what it's been developed by AI. Fine, there is AI-based structural model that is developed that will inform, for example, a resource estimation. Who is going to sign off that that resource estimation is reliable because AI generated it? I mean, I know that our experience right now is based on how AI is performing as of today, which there is a lot of false positive, right? There is a lot of weird answers that it's giving you. It means, as I said earlier, in 6 months' time, we have generative AI that learns itself and will be like a full-blown structural geologist or geological engineer, and they can work by themselves somehow. But there still has to be somebody that goes and takes pictures, or does a little, at least the first round of mapping. So yeah, it's gonna be interesting to see the next 6 months, a year, what they're going to bring. I still feel like that the human intervention is still required.
Just one point which applies to also things like imago and image learning is that the vast majority, 99.9% of the drilling for most of the projects we're working on has been done. It's done, and the core may not even exist. So if we are lucky enough to do core scanning or hyperspectral scanning or use AR on core, again, it's going to be for a tiny fraction per deposit of drilling or the mining phase. So then we end up at the door where how do you merge that hyper detailed, dense data set with something that is basically analog and historical? And that to me is actually a big issue. Going forward, sure, I can see everything's going to be scanned and AR'd and logged with a machine, no problem. But how many mines do we know that's doing that from the get-go, right from day one, from discovery hole? Not many. So as this gets going, as this gets traction, I can see it coming along. But right now we're in a bit of a transition phase where we're sitting on a pile of legacy analog data that we have to somehow marry with this super interesting future technology.
All right, wonderful. Thank you for that, and thank you for all the questions about AI. There was a couple of them, and hopefully we covered all of those with those answers. We've got a couple more live questions here. Let's go to this one. This one references the Canadian Shield, but I think we can apply this to pretty much anywhere. In hard rock open mining within the Canadian Shield, is it more common or more recommended to build separate models for large-scale structures or bench-scale features like joints and minor faults, or to combine them into a single model for planning and stability analysis? And I would say that this could be applicable to anywhere in the world. But thank you for the question. Good question. How about one of the Canadians to start? Luca.
Okay, to answer this question, I go personal. So I normally I normally create a single model because every structure creates, it's part of the same system, like without getting too crazy with the minor faults or with the specific joints, but there is a relationship between faults, joints, and geology. So I tend to go for a single model, and then that has the ability then to be broken down based on the end user. So you go with a big model in the assumption that the model is used for detailed slope design. Okay, because if it's just for early stages, then I would just stop at the large scale structures. But if we're talking about the example of design, the idea is to highlight all the structures that could have an impact to the design. And so that would entail large scale structures and secondary structures as well. Now with the joints, it depends on the case. If we're talking about joints in which it's easily pick out from either the open pit, like the exposures, or from data that you have continuous shear joints or joints that you can represent as a wireframe, then fine, they could be represented as such. But if the joint system has a direct impact on the slope stability, then we would combine the large-scale structural model and use DFN. I've seen a question coming up. They use DFN to assist in the definition of the secondary structures, like joints, minor joints, or segmented joint systems, or segmented secondary structures that could have an impact on 1 or 2 bench scales. So it really depends on the objective of the model, but the approach that I normally use is try to combine everything as much as realistic, because each structure is part of that same system. It can tell a specific story, especially because sometimes if we're talking about the Canadian Shield specifically, sometimes it's your joints that are giving you much headache than the structure. Sometimes you have large-scale structure that, for example, for hydrogeological purposes, for substability purposes, your large-scale structures are not conductive, and you have one single joint that is wreak havoc on your hydrogeological system. So we try to combine a single model to help whoever needs to use the model to get what they need for their specific scopes.
Yeah, no, I'd agree with that. I think it's not very common that, in certainly in my experience, that you would be doing both a full structural model for the system and then also the doing the bench scale joints models. It's a different real focus on when you and detail that you need to apply to do the joint and minor fault mapping. Look, I certainly in South America we tend to do a lot more detailed joint type mapping. In the Canadian Shield, the work that we've been done in the various mines in North America has really been more focused on large scale structural systems and understanding that. Sometimes there's just not enough time to build that amount of resolution. So it's also very important to understand the continuity of your joint systems and make and are they really relevant for the stability of that pit? Yeah, I think it really depends.
All right. Very good. Well, thank you for the question. Let's go to another live one. This one is about DFN, discrete fracture network modeling. I think Ian brought this up earlier. Some field experts remain skeptical about using discrete fracture network modeling DFNs in open pit operations. How do you see the role of DFN evolving in mine planning compared to traditional approaches like limit equilibrium analysis?
Well, I can start, given the fact that I work in close collaboration with our DFN team in my group, and we work together. I'm saying in here, being biased towards DFN, meaning that I do like the approach because it provides a little bit more realism in the analysis of your rock masses. Allow me to use this. I guess I'm not a geotechnical engineer, but when I see a lot of like limit equilibrium analysis used for open pit design in hard rock, my mind blows up a little bit because we are like assuming a lot of continuity in structures and in the system that it actually is in reality. And we're going down the path of creating this weird formula to calculate rock bridges, to understand continuity of things, and then we do all of this beautiful math, and then we're throwing it into a software that consider everything continuous. So we're playing it. Whereas by shifting into DFN, we could start playing with scenarios of possible, configuration in terms of continuity, interaction of the different joint systems. Obviously, there is, you have to handle that with care because you need to have the actual data that will allow you to do that. So it depends very much on the data that you have available. Where you have a good amount of data that would allow to go down the path of a discrete fracture network, that would be advisable because in that case, you're building in more realism into your modeling. When you don't have enough information, then you shouldn't even consider DFN because then you can, go down the path of something that is not usable or not realistic at all. So with everything, know what you're doing, have the correct amount of information that you need, a robust structural model, enough information that you can build a DFN. So not only like your fracture frequency, but also your continuity. So do the mapping, do the scan line, which is the other thing that it's, we tend to not do it that often, like do a lot of scan lines, do a lot of window mapping, get your continuities on your larger scale structure and your small scale structure. And then consider using DFN because then you create a little bit more realism, or at least you can test scenarios to understand what is the most probable conditions in terms of structural setting, like joint systems, that your slope has, and you can, plan or run analysis accordingly. So I am a big advocate of DFN just because it brings more realism in your analysis.
So sorry, Luca. So can DFN evolve further, or is it where it is?
No, it's evolving still. It's evolving.
How
still.
can it?
Yeah.
How could it evolve further?
So it's evolving by AI again, which you can start. You increase the amount of the stochastic approach that you can use, and then it's evolving in a way in which you can see even now other major companies like Rock Science and right now even Itasca, they're moving towards, instead of like using ubiquitous jointing or limit equilibrium analysis, they're starting to say, okay, let's build a DFN and use that one in our analysis instead of like assuming, ubiquitous continuous structures everywhere. So it's evolving in a way that it's getting embedded in all the primary numerical simulation tools that are used. And then, and it's a way to sort of like help understanding the secondary and small scale structure distribution. And right now, actually, it's pushed to a start of understand even the major structures. I've seen some of the modeling software for oil and gas, the SCUA, for example, in which you can start applying DFN tools to model fault systems when the data is sparse and to do more like a stochastic way of developing your fault zones and such. So it is the concept is pretty much the same, but it's building up. You're creating more robust, let's say, DFN tools. There is a lot of assumption. Don't get me wrong. It's not like the magic recipe that solves all our issues, right? Absolutely not, because it's tied to your structural interpretation. So if your major structures are wrong or you're messed up with the conceptual structural understanding, your DFN would be impacted by that. So we always go back to, the important thing is know your deposit, know what is happening in there, and try to go as deep as you can given the data and your understanding of your deposit before you go into more detailed stuff like discrete fracture network. But if you do, it helps a lot in getting more more realism, as I said earlier. And the other trick is that, you can hear in the industry that everyone that deals with open pit, they want steeper slope. there is no way that you can get steeper slope if we keep using limit equilibrium analysis or S-wedge. You know what I mean? I know that some of the geotech online will just get pretty nerd tense in what I'm just said, but allow me to use this sort of like simplification just to say that if we want to get, if you want to go steeper, especially when the geological complexity is higher, we need a little bit to push the envelope a little bit with more sophisticated way of doing the analysis. But again, know your deposit. If you know the geology with all the uncertainties that comes in, then you can handle it. Otherwise, it would be, it would be same as with Leapfrog or same as with other DFN tools or any fancy geostatistical geological model. It would be still garbage, but made in a fancier way if you don't really know what you're dealing with.
Yeah, I guess, Luca, if I'm right on this, right? So it's how would it evolve? And it's the application of AI or being able to characterize form lines on imagery like LiDAR, photogrammetry, AI being used to tell a viewer for the classifications, AI being used into seismic work, right? I think that's what you're suggesting, right? That sort of input of AI can help evolve information to help inform the DFN.
Basically, yes, because the concept of DFN is relatively simple, and it's just a way of that it gets modeled up. But the important thing is having all the input data correctly, so you can build your DFN model, because it is a powerful tool that will allow you to test scenario, look for possible area with a higher probability of failure, right? And so that would be another nice way of moving away maybe from the factor of safety and start thinking about probability of failure. But that's a discussion for a whole different webinar. And but that is sort of like a way to sort of bring it to the next level. And AI could just help a lot in getting all the information that are needed for like a robust DFN model. And in turn, a robust structural model too, structural interpretation and structural model.
All right, very interesting discussion. Thank you, Luca, for that background. Thank you for the question. Let's jump to this one. This is an interesting question. This is a good opportunity for people to jump on their soapboxes if you so choose. What fundamental concepts or practices in structural geology do you see most underutilized or omitted, or I guess absent, in mining? And I know that Jeff had a couple presentations on this in the structure course. So maybe Jeff, if you want to kick this one off, underutilized practices or concepts.
Oh, okay. I'm gonna have to rack my brain and try to remember what those were. But one thing that I'll just throw out one item right now and maybe try to think a bit more here. But one item I think is not well utilized in the industry is actual structural interpretation of core. I think we're pretty good at having consultants and geos collecting point data. If it's broken, the information is collected. It's a fracture, it's a fault, it's a joint. But one thing I've seen just on my experience, a number of operations, there isn't somebody there that's actually laying out the core and actually taking the time to do a full structural interpretation, even if it's brittle ductile or something that's cohesive, relating it to mineralization, relating it to alteration. And so I think that is my feeling anyways for a lot of logging, unless you have like a specialist come in. I feel like that's something that a lot of operations there's an opportunity to improve that for a number of areas for data collection. And then the templates, that'll be the second point I'll put in right now, is a lot of projects I've had an opportunity to work on. It's, great intentions are there. You want to collect faults and fault zones. But again, it's try and take that next step to really, you're spending the time to collect the data, but you can also really increase the value of the data that's being collected. And it's to that point again of, well, what is the actual damage zone to this? What is the core infill zone of this? What is the characteristics? I just feel like there's a lot of templates and stuff that you can use to help or that we use anyways to help try to collect a lot more information when you're actually spending the time with the core. I'll pass over to somebody else, then I'll think of it more.
Yeah, thanks, Joel.
Yeah, we got to throw in. I think this is a good question. One of the things that I see all the time is that the geologists go down underground and they take measurements, right? They just take measurements. What we're missing here is two things. One, we need to make sure we're taking the right measurements to understand the deformation history of this particular rock mass, so that we have enough information to understand the overall system. What are the patterns and what are the patterns of this rock, right? And every rock system, depending on its deformation, has different patterns. And if we understand what those patterns are within the rock mass, then we've got a very good conceptual understanding of what the rock mass looks like, right? And so I think that's one very important point to focus on. And the other is that to be practical, in many cases, the mines need to know what their domains are. And the geologists can add huge value by by identifying domains within the mines. And I don't see that done very often at all. That's my 2 cents.
I'd just like to make 2 points. The first is that, every mine is unique. So if you can, as a structural geologist, go to site, look at the core, and build up a standard operating procedure for logging structurally relevant patterns, as Wayne says. That's the right word, patterns. So, and be very specific. Get an atlas, get an almanac down, get a core library, not just of lithologies, but of foliations, minor fold axes, etc. So, be prescriptive to try and bring that kind of logging, that structural logging or structurally relevant logging, to maturity, and then do some logging yourself, because you need to have a benchmark to compare the logging, and the other data, whether it's remote sensing or UAV derived or AR derived or whatever. Data to what you've measured. So it's really about patterns, as Wayne says. That's the right word, and about context, I think. The other thing that I wanted to say, I was trying to remember, I started with 2 things, then I forgot the second thing, is the biases in drilling will produce biases in the data that you collect. Let's say you're looking at ATV data, chances are that the person that's doing the picks is going to pick much higher alpha angles more regularly, but much lower angle alpha structures less frequently. So there's a bias built into the way that the drilling has been done, and there's a bias built into which face of the pit that you map. So be aware of the biases in the data collection, which again comes back to your structural setting and the patterns in the rock. I think that's enough for now.
All right, very good. Good. I think this next question is a nice piggyback off that one. How do you balance traditional field mapping with modern digital tools in data collection? I think these modern tools would be something like photogrammetry surveys, point clouds, and so on. I know I hear this a lot when I go to mine sites, that some people don't really like going out into the field anymore to map, but it is very important. So how do we balance that?
Right. Yeah, well, this is close to my heart, I guess. But I mean, I don't see it's hard. I don't see it being hard to balance. You've got the new tools that are coming online, hyperspectral data, the drone imagery, these are all things that are going to help us get understanding faster, as well as getting a higher resolution on what we're dealing with. Our traditional tools and traditional field mapping, just ways to verify that the new data we're getting is reliable. Ultimately, I suspect some of our typical tools that we use are going to become obsolete, and that's where it's going to go. I still don't believe that, however, that the geologist should do everything remotely. That there should always be verification by going up to the rock face and licking it to see what it tastes like. Okay.
Good advice.
I mean, just to add what Wayne said, one of the things that it's very hard from, digital or from understanding from your desk is to look at kinematic indicator of a fault plane. That is something that, I mean, unless you fly the drone exactly on the fault plane, and that is actually the one of the risks that I've seen happening in a couple of occasions now, in which displacement and structural pattern and a conceptual model was built by simply looking at apparent displacement on an open pit or on an outcrop, which sometimes is just purely apparent. And they, the classic example, everything interpret to be a normal fault system when it was just actually a strike slip system. So they ended up messing up everything because nobody went to the field and look at the fault planes, right? So they are two tools, digital tools. It's in the name. It's a tool. It's something that will help you to close the gaps on something that you were not able to see in the field for multiple reasons. But there's still the need to go and just look at, as Wayne said, just look at the fault, look at the area, like try and work out what is happening from the field as well.
Yeah, I feel like I'm going to be a broken record here, but what some of the things we do is we're bringing in these digital data collection tools. Somebody sits in the office, does it as much as they can, but there's always this check where they're required once or twice a month to head out to the field and just double check that digital data collection they've had from the desktop matches what is observed in the field. And then for myself, just in terms of data collection, there's always a conversation about like just paper data collection historically versus everything being done on a tablet. And maybe it's just me. I cannot get away from at least doing some paper mapping. And so for me, I love being able to just draw, do my own little stair units on a notebook, draw what I'm visualizing on the wall, and being able to digitize that for people to look at or for myself to understand later. I still personally think there's a lot of value in that side of things for data collection, that interpretation on paper. But the reason obviously for the digital collection platform makes a lot of sense. And that's just, you need to make sure that people are collecting something that's very standardized for the broad majority of people that are working in the operation. So just to me, I think the two can kind of complement one another. And if you have someone who's a bit more of a structural nerd, having them with a pen and paper and doing the interpretations, I still encourage that. I like it.
Yeah, great comments. If I might just add my personal experience going back and forth between field mapping and largely photogrammetry mapping. Often when I would go into the field, I would see all the small scale, the minutia that would actually guide what I look for in the photogrammetry model as well. So that was very, very helpful, and things that you wouldn't notice in the photogrammetry model, but you can sometimes see them. You just need to get that field perspective to actually see what you're looking at in the photogrammetry model. So great. Thank you all for that. We've got time for one more question. We'll go to this live one. How do you handle structural complexity in areas with multiple deformation events or overprinting features? And if I recall, I think this is a topic that Ian covers quite extensively in some of his presentations. So maybe I'll kick it over to you, Ian.
I wasn't really expecting that to land on my lap. I need to think about that. Yeah, structural complexity. Well, the first thing to understand is that you're mapping in a system. So structural geology is, what is the word? It's not fractal, it's scalar, right? So what you see at the big scale, you should see at the small scale. So if you understand at the larger scale what, for instance, the geometry of your folds might be, are they recumbent isoclinal, are they closed and upright, etc., you're already on the front foot in terms of what you might expect in the pit. Also, always understand that every terrain has its own DNA. So it's gone through a pressure, temperature, time loop. It might have gone up to 600-700 degrees Celsius, 7 kilobar, and then come down through a retrograde event. Things that are more competent may have boudinaged and pipped, and you may have low pressure shadows where you've got retrograde minerals around the edges of those. So again, it comes back to understanding the system that you're working in and the mill that it's been the sausage machine that it's been through. Once you really understand that, and you can do that from looking at your regional geophysics, reading up about it, try and understand what your regional kinematics and deformation events are before you go to site. So we always add 2 or 3 days into our quotes for background review. We've got we're online with Scopus and Science Direct. We've got guys in the office that are doing their degree, so we have access to the libraries at the universities. Try and read up before you get into the area and have a little, as Jeff says, have a little sketch in your mind as to what what the major events are, what the rock types are, how they might be reacting. So the other thing, I've got a very strange way of thinking about rocks. I always think about how did this thing absorb stress? And if you can think a bit like an engineer in that respect, even though you're not, and think, that was more competent, so that would have pipped and boudinaged, and this was less competent. And so on. If you can get your mind to that state of thinking, it often really helps you to understand the features that you might see in tectonostratigraphy. So that's the way we handle it at Tech, is do a bit of background research. Don't go in blind. Okay, don't climb off the plane and think you're going to do some productive mapping. School yourself first as to what's happened before you get there. There'll always be overprinting features. Usually they're brittle because tectonics tends to outlast the heating phase of an origin, normally on any given Sunday. So there's usually a brittle ductile and then a brittle overprint. So expect that as well and figure out how that might have propagated through your tectonostratigraphy or been inflected by contacts. Also think in terms of competency contrasts, right? So something stiffer against something more ductile is going to have, there's going to be shearing between them. So try and put yourself boil yourself down to an ant and say, what would have happened in this particular contact or in this particular rock type while it was deformed? And very often you start to see things, and that'll get you moving forward. Bit of a knack, but if you do it often, it kind of comes naturally after a while. I don't know. Anyone else got anything to say about that?
Great.
Well, maybe. No, that's good. And maybe also just being really systematic about one outcrop to the next one, documenting, trying to understand that outcrop, and then try to relate it back to the previous outcrop. And how does this make sense? What are the relationships between what you're seeing on this outcrop versus that outcrop? And I think it's just a systematic and careful process. It could be complex, and yes, it could be challenging, but keep calm and collect the data.
Yeah, I was gonna say that on the same lines. Maybe not keeping calm, right? More calm than I am out there. So, but I think one trick for structurally complex areas, I imagine, like just for a folding environment, Ian and Wayne were alluding to, sometimes I find that as soon as I can understand what a fold axial surface is for one sort of deformational event, it kind of helps guide my mapping a little bit, just kind of where I am, be like, oh, okay, now I'm in a D2, now I'm in a D3, and try and understand, like from one outcrop, like William was saying, one outcrop to the next, what is the sort of pervasive deformational style for this area? And then it is, it's really important to, as Ian said, get the small scale stuff to help represent it on a larger scale. But then it's also that challenge of not being bogged down too much with that small scale stuff, right? And that's trying to extrapolate, okay, what is the important wavelength or amplitude of this that I'm interested in looking at? So yeah, just more, I guess, just saying along the lines of what the others have already said.
The worst feeling as a structural geologist when you're mapping is having the shudder go down your back when you realize that the amount of drilling that they've done is nowhere near enough to represent the complexity that you're seeing. And that to me is always a moment when I start sweating and going, oh geez, kind of thing. It's just something that happens and you go, oh man. Anyway.
And just to add one thing, and I'm guilty of that multiple times, just when things get too complex or things don't make sense, or if you feel like you hit the wall, ask for help. There are always people that might be able to have more experience in specific terrain than you have, or to handle with specific situations. Just, sometimes we tend to be afraid of doing that, but we shouldn't. We should just simply say, okay, I'm hitting a wall. Let's brainstorm and find a way to either improve the way that we can collect data or make sense of the data that we've collected. Because we don't know everything, so it's ask for help.
Yeah, so that's a brilliant point. Never map alone, especially at the beginning. Map in a team of 2 or 3 people, because just like looking at core, you'll see different things and you'll say, hey, you're biasing yourself, you're measuring too many of that feature. What about this feature? If you look over here, you can see something a bit different. So, never map it at the start, at least on your own. Map in a team, so you'll all see different things.
James, can I know we're at time.
Yeah,
there's one comment that Ian said there I thought was so great, is like if he gets into the fear that there isn't enough drilling. And one thing I think could be good for the sites is if you can, to the point of domaining, like it's been talked about before, if you get into a structurally complex area, sometimes what really helps is to take a domain and say, this is predictably unpredictable, and whereas this area is predictable. And the importance for that is, okay, fine, on the short-term KPIs, if you're looking for a resource, does it actually matter to your mind? If it does, put more drilling into it. But if it's just predictably unpredictable for a certain amount of time, and you know that your KPIs are going to be fine on an annual basis, is it actually worth it? That's probably another conversation, but I just really like that comment that Ian said, and the fear that we all have. So I want to toss that in quickly.
No, I appreciate that. I'm gonna have to cut us off, unfortunately, but I didn't want to cut us off right at 12:30 because that was a really great conversation. So really appreciate that, guys. Just really quickly before we wrap up, couple quick plugs. One for our Fundamentals of Open Pit Slope Designs course. This is a fantastic course. We're going to run it for the second time starting in September, on September 16th. So really, really soon. If you'd like to register for that, you can scan the QR code here, or you can find us online and sign up there as well. And also, we've got a new course coming out, Blasting and Pit Slope Performance, and that will be released on September 23rd, so shortly after. So you can scan that QR code or find it on our website as well. And with that, I want to thank all the panelists again so much for your time. Really great conversation, and thanks to everyone who tuned in today. It's really, really fun.
Thank you all.
Thanks, everybody. Great discussion.
Thank you.
Okay, take care, everybody.
Bye.